Welcome to today's paper reading. Today's paper is titled, Pre-trained Large Language Models for Industrial Control. This paper was published on AR14 by Lei Song and colleagues from Microsoft Research Asia. The abstract highlights the appeal of developing high-performance controllers for industrial control with minimal sample usage and technical debt. It introduces the concept of foundation models, which are powerful due to their pre-training on extensive corpora, and explores their potential in industrial control. Specifically, the abstract discusses the application of GPT-4 in controlling HVAC systems, outlining the experimental design to evaluate its performance and generalization capabilities. The findings suggest that GPT-4 can achieve performance comparable to reinforcement learning methods but with fewer samples and lower technical debt, indicating a promising direction for applying foundation models to industrial control tasks. Reinforcement learning, RL, faces significant challenges in sample inefficiency and high training costs, which are particularly problematic in single-task learning scenarios. In industrial control tasks, such as inventory management and HVAC control, there is a need for high-performance controllers that can be developed with minimal technical debt and tuning. Foundation models, pre-trained on large, diverse datasets, offer a promising solution by providing rich prior knowledge that can be adapted to various industrial control tasks. These models demonstrate powerful emergent abilities and fast adaptation to new tasks, making them a valuable resource for addressing the challenges in industrial control. The foundation models, which are pre-trained on large-scale data, serve as the basis for various downstream tasks. These models, such as BERT and ChatGPT, utilize a transformer structure that relies on the attention mechanism. Large language models, LLMs, like GPT-4 are benchmarked for their performance in specific tasks, often outperforming open-source models. In decision-making scenarios, these models can leverage their rich prior knowledge to interact with off-the-shelf LLMs, addressing issues of executability and correctness through mechanisms like semantic translation and modular generation processes. Figure 1 depicts the pipeline for utilizing GPT-4 to control HVAC systems. The process begins with a pre-trained large language model, LLM, that generates corresponding actions based on a prompt. This prompt includes a description of the current state, simple HVAC control instructions, and relevant demonstrations. The interactive environment or simulator then executes these actions and provides feedback. To facilitate better understanding by the LLM, a translator component converts numeric state vectors into natural language representations. This pipeline ensures that GPT-4 can effectively manage HVAC systems by leveraging its language processing capabilities. The method employs a pre-trained large language model, LLM, as the decision maker for HVAC control. This LLM generates actions based on prompts that include descriptions of the current state, HVAC control instructions, and demonstrations of relevant states. The environment used for this process is the Bian simulator, which requires parameters such as building type and weather condition to create an interactive setting. The state in this environment is represented by a numeric vector detailing room temperatures and external conditions. The primary goal is to maintain room temperatures close to 22 degrees Celsius while minimizing energy consumption. This is achieved through a reward function that balances comfort and energy consumption, using a hyperparameter alpha to adjust the balance. Figure 2 illustrates the process of generating prompts for controlling HVAC systems using a pre-trained large language model, LLM. The LLM, acting as the decision maker, generates actions in response to prompts that include descriptions of the current state, HVAC control instructions, and relevant state demonstrations. The environment, such as Bian, executes these actions and provides feedback in the form of numeric state vectors. To facilitate the LLM's understanding, a translator component converts these numeric states into natural language representations, retaining all relevant information. This process ensures that the LLM can effectively learn and apply HVAC control strategies across various building types and weather conditions. In evaluating GPT-4's performance in HVAC control, we found it to be comparable to or better than PPO, especially when provided with demonstrations relevant to the target scenario. Notably, GPT-4 achieved its best performance when learning solely from historical interactions with the target environment. The impact of different types of demonstrations was significant. Historical demonstrations were the most effective, while expert demonstrations consistently diminished performance. Representative demonstrations provided a slight improvement, but only with an appropriate number. Regarding comments and instructions, manual comments significantly improved performance, whereas self-comments had a detrimental effect. Task descriptions were found to enhance GPT-4's performance more than task instructions, which could potentially mislead the model. Figure 3 illustrates that even under the same weather condition, different buildings exhibit distinct expert policies. This observation underscores the variability in HVAC control strategies across various building types, highlighting the importance of context-specific demonstrations. The figure visually represents how expert policies diverge, emphasizing the need for tailored approaches in HVAC control systems. Figure 4 illustrates how the same building employs different expert policies under varying weather conditions. This highlights the adaptability and necessity of tailored strategies to optimize building operations and efficiency based on external environmental factors. Table 1 presents the performance of GPT-4 in controlling HVAC systems given different sets of expert demonstrations. The table shows the results for scenarios within Group X, where X can be AF, using abbreviations H, E, and R for historical, expert, and representative demonstrations, respectively. The number following these abbreviations indicates the count of corresponding demonstrations in the prompt. GPT-4's performance is compared against PPO, MPC, and random policies, demonstrating its ability to learn HVAC control principles from diverse demonstrations. Table 2 presents the performance of GPT-4 using various types and numbers of demonstrations. The results show that historical demonstrations are the most effective for GPT-4's decision-making. Conversely, expert demonstrations consistently reduce GPT-4's performance, sometimes even worse than no demonstrations at all. Representative demonstrations can slightly enhance GPT-4's performance, but only if the correct number of demonstrations is provided. This indicates GPT-4's capability to learn from both good and flawed demonstrations, verifying its reasoning abilities. Table 3 illustrates the impact of different types of comments on GPT-4's performance. The results show that manual comments significantly enhance performance, raising it from 0.99 to 1.16. Conversely, self-comments tend to degrade performance, lowering it to 0.59. Interestingly, a combination of manual and self-comments results in a performance of 1.11, suggesting a potential balance effect. This table highlights the importance of comment quality in improving GPT-4's learning capabilities. Table 4 presents the performance metrics of GPT-4 when using different types of task descriptions and instructions. The results indicate that the inclusion of a task description alone significantly enhances GPT-4's performance, achieving a mean reward of 1.12 with a standard deviation of 0.04. In contrast, using only task instructions yields a mean reward of 1.04 with a standard deviation of 0.01. When both descriptions and instructions are used together, the mean reward is 1.07 with a standard deviation of 0.03. Notably, the absence of any descriptions or instructions results in the lowest mean reward of 1.01 with a higher standard deviation of 0.08. These findings underscore the importance of clear task descriptions in optimizing GPT-4's performance. Table 5 illustrates the impact of rounding real numbers on GPT-4's performance in prompts. The table shows that when real numbers are rounded, GPT-4 achieves a mean reward of 1.16 with a standard deviation of 0.04. In contrast, without rounding, the mean reward is 1.07 with a higher standard deviation of 0.07. This data confirms that rounding real numbers can indeed enhance GPT-4's performance, supporting the hypothesis that GPT-4 handles rounded numbers more effectively. This finding is significant for optimizing prompts to maximize GPT-4's performance in tasks requiring numerical precision. Table 6 presents the performances of proximal policy optimization, PPO, and GPT models under weather perturbations. The robustness of GPT-4 policies is tested by introducing noise to the external temperature, sampled from a normal distribution with a mean of 0 and a standard deviation of 2. The results show that GPT-4 can maintain good performance in the presence of perturbations without a significant decrease. PPO results are also included for comparison, along with results from previous sections without perturbations. The potential of using large language models, LLMs, for decision-making has been demonstrated, but these models heavily rely on their reasoning capabilities. Unlike reinforcement learning, RL, algorithms, which can improve through interactions with their environments, LLMs lack self-learning capabilities. However, LLMs can accumulate knowledge across various tasks, unlike traditional RL algorithms, which rarely generalize across different tasks. A significant challenge is enabling LLMs to learn autonomously. Existing works are categorized based on whether a pre-trained LLM is leveraged, whether the model can learn continually, whether the LLM is updated, and whether the upstream or downstream is updated. Key aspects for decision-making include data quality demand, data efficiency, and online learning. Figure 5 illustrates three distinct paradigms aimed at achieving learning capabilities and decision-making tasks without directly fine-tuning large language models, LLMs. The first paradigm, standard RL, involves a trainable component, typically an RL agent, directly interacting with the domain environment. The second paradigm, trainable downstream components, sees LLMs acting as intermediaries between the domain environment and trainable components, where LLMs receive prompts from the environment and provide inputs to the trainable components, which then optimize actions for the environment. The third paradigm, trainable upstream components, differs in that the RL agent interacts with LLMs by providing prompts, and LLMs communicate with the domain environment by offering actions corresponding to the given prompts. This figure contrasts these approaches with standard RL algorithms that do not incorporate LLMs, highlighting the varying interaction pipelines and the role of LLMs in each paradigm. Table 7 provides a comprehensive comparison of various approaches to achieving learning capability in decision-making problems. The table evaluates these methods across several key aspects: data quality demand, DQ demand, which assesses the data quality each approach requires; data efficiency, focusing on the ability to perform well with zero-shot or few-shot learning; and online learning, which measures the capability to adapt quickly to recent changes. Additionally, the table considers generalization/transfer learning, performance, interpretability, and LLM's accessibility. Each aspect is rated with plus symbols, indicating better capability. The table highlights the strengths and weaknesses of traditional decision-making methods, in-context learning, LLM fine-tuning, and training upstream/downstream modules of LLMs, providing valuable insights for decision-making in various scenarios. In this paper, the authors demonstrate the effectiveness of large language models, LLMs, when integrated with existing decision-making approaches in industrial control optimization. The experiments show that incorporating LLMs significantly enhances the generalization and robustness of traditional methods, potentially scaling to a wider range of scenarios with reduced training effort. However, LLMs exhibit certain limitations in industrial control optimization, such as a lack of adaptation capability to environmental changes and the ability to learn and forget selectively. The authors also investigate techniques to augment LLM's capabilities in these areas. As future work, they aim to further explore the potential of LLMs in various industrial domains and develop a comprehensive framework that combines LLMs with existing approaches to address a wide array of control optimization challenges in the industry. Thank you for watching.